we left off with piecewise functions, right? We graphed a couple of them, and you guys were doing okay, but not amazing with it, so I think we need a few more. So let's practice. This one I'm going to have us graph it, and then I'm also going to ask some questions about it. So the first question, there's some on the homework like this. Before I ever graph, I'm asking you to find f of 0, f of 1, and f of 2. Now it's a function. That means when you plug something in, you can only get one answer out. So when I do f of 0, there can only be one answer. So if you put in a 0, which of these three things do we use? The top, because 0 is between -3 and 1. So when I find f of 0, I have to plug it into the top piece, so the opposite of 0 plus 1, which is 1. When I ask for f of 1, which of the three pieces do I put it into? First, second, and third. Second one. And you get out 2 if x equals 1. So the only thing I get out is 2. F of 2. So when x is 2, which piece am I on? The third. So we get out x squared, so 2 squared is 4. So sometimes I might ask you to evaluate from a piecewise function, and you just have to figure out which piece you're plugging it into, and then replace your x to get your answer. Let's wait until after we graph it to do the domain and range. So when we graphed these piecewise functions yesterday, I told you you had to have a t-chart for each piece. So when I do that first piece, what values am I going to have to plug in for x?
-3.
Yeah, make sure you're with me. I'm going to give you guys time to work on homework. Please stay with me on the notes right now. We have to put in the -3 and the 1 because those are two endpoints here. Then if you want, you can plug in something else between them, so maybe a 0. So if I put in -3, the opposite of -3 is 3, plus 1 is 4. We put in a 0, we get 1. Put in 1, opposite of 1, -1 plus 1 is 0. When I go to graph these, are they both closed circles? No. The 1 would be open. Since it had 2 endpoints, it's not going to continue in either direction. So we have -3, 4, 0, 1, 1, 0 is open, but those are 2 endpoints, so it's just connecting those. The second piece, 2 if x equals 1. How do I graph that? If you made a t-chart, what could you plug in for x? 1, that's the only thing. What do you get out? It's just a single point on the graph. 1, 2. Third one. X squared if x is greater than 1. So we have to start by plugging in a 1. And that one just keeps going. So maybe a 2 and a 3. Since it didn't have an equal to, it would be an open circle at 1. So 1 squared is 1, 2 squared is 4, 3 squared is 9. So 1, 1 is open, 2, 4, 3, 9. So we're getting part of a parabola here. I'm sure your graph is probably a little prettier than mine. Questions there? All right, so now, can we get the domain and range movement? domain. We go left to right. Where does this graph start? -3. And we stay there until this piece ends at 1, but I have a green dot there, and then the blue one picks up and keeps going. So what's my domain? What's the range? And the 0 will get a parenthesis because it's an open circle there. This time I didn't ask you where it was continuous. I just said, is it continuous on its entire domain? Is this whole graph continuous? No, we've got a break in our graph when x equals 1. So the whole thing is not continuous. Questions on that? I want you guys to try this one. See if you can figure out what it would look like. So I'm not sure that we have this graph drawn correctly. So this first piece, it's saying 2x as long as x does not equal 0. So x could be anything else you wanted to plug in. So you could put in, you know, a -2, a -1, a 1, a 2. You still really should plug in a 0, but what happens when you plug in a 0? What would it be? It would be an open circle since it's not equal to. Okay, so then you can plug in anything else. If I put in these numbers, 2 times -2 is -4, 2 times -1 is -2, 2 times 0 is 0, 2 times 1 is 2, 2 times 2 is 4. If I plot them, -2, -4, -1, -2. 0, 0 was open. 1, 2, 2, 4. So this is a line with an open circle in the middle. So right there at the origin, that's an open circle. And then the second piece is 1 if x equals 0. What's that? Yeah, just a point at 0, 1. So it still function, passes the vertical line test because that's open right there. So when I say f of 0, if you plug in 0, what do you get out? 1. F of 1. So 1 does not equal 0, so you put it in the first piece. So 2 times 1 is 2. F of 2, so you put it in the first one. 2 times 2. Domain, if I look at my graph, what x values get covered? All of them. Range, what y values do we use? all of them except 0 because it's an open circle. So our range is negative infinity to 0, union 0 to infinity. Everything except that one number. Is this graph continuous? No. A lot of times those piecewise functions are not. We did see one yesterday where the two pieces lined up and it was a continuous function, but if the pieces don't match, it's not. All right, any questions there? All right, everybody's favorite, the greatest integer. So this is typed kind of funny, but it's like a double barred bracket here. So do you guys remember what the greatest integer looks like? Okay. I am going to actually, I'll use it. Okay. When I do a greatest integer function says you can only get out integer values and you can't get anything bigger than what you put in. So if I put in a 0, 0 is an integer, I get that out. If I put in 0.5, 0.5 falls between 0 and 1. What's the smaller of those two numbers? 0. If I put in 0.9, 0.9 is between 0 and 1. You always get the smaller one back, so it's still giving me 0. But what happens when I plug in a 1? You get 1 out because 1's an integer. Okay, I'm going to adjust this because I need my graph to be big enough to actually see what we're talking about. So I'm going to maybe I'm going to stretch up my graph a little bit. Alright, so we put in 0, we got out 0. Put in a half, we're still getting out 0. We put in 0.9, we're still getting out 0. But as soon as we put in 1, we get out 1. So we're down here on this step all the way until 1. If you put in 0.99, what are you going to get out? 0. If I put in 0.9999999, I'm still getting 0. So this stays down here all the way until it hits 1 exactly. So what we do is put an open circle at 1. And then we jump up to the next step. And I'm going to stay here until I get to 2. So then you would have an open circle at 2. And then once you put in 2, you jump up to the next step. And you can continue your pattern the other way as well. So the greatest integer function, that's your step function. Okay, it looks like this and just keeps going. Do you guys remember seeing this one before? Did you not get to it last year? Okay. If I wanted to talk about the domain, what x values does this one hit? All of them. The range, what y's do we hit? I don't hit every single y value, do I? It's like -3, -2, -1, 0, 1, 2, 3. So there's different ways to write your range. Since it's not a constant, you could, put ... show there were points before this and start listing some. And then ... show it keeps going. Or you could write out integers. We hit every integer value. Do you guys remember, did you ever talk about the symbol for integers? If you use a double barred Z, that's a shortcut. It means integers. It's like the double R means all real numbers. So lots of different ways that you could give that range. to practice graphing another one of these. So this is the greatest integer, and again, when I type it, it looks a little weird. A lot of times looks like this. So the greatest integer of x plus 2. If you can figure out what one step looks like, then you can get the rest of the graph from it. So start with an integer value. If you plug in 0, 0 plus 2 is 2. The greatest integer of 2 is 2. So if I'm plotting this, I have a point at 0, 2. Okay, we have to put in decimals and fractions when we do this. So I just like the decimals. I'll go with 0.5. So if I plug in 0.5, then I get 2.5. Greatest integer of 2.5 is still 2. So when I put in a half, I'm still getting out 2. If I put in 0.9, I get 2.9. Greatest integer of that is still 2. But what happens when I put in a 1? We get 3 out. So 1, 3 is the beginning of the next step. So you put an open circle right underneath that so we can see the step is just 1 unit long, and you jump up 1. So we'll stay on this step until we get to 2, and then we would jump up. My rule is going to be when you have to draw a greatest integer function, I want to see a minimum of 3 complete steps drawn. Okay, I don't care which 3, if you do it this way or if you extend it the other way. You can do more. More is always better. But minimum of 3, and then because this graph doesn't stop, it keeps going, I want you to put dot, dot, dot on each end, just to show that this pattern continues. This seems like kind of a weird function, but it actually does come up in real life situations, like if you think about the post office. If you go to mail a letter, as long as the weight is under a certain amount, you just have to buy 1 stamp, right? But then if your envelope is a little too heavy, you have to buy a 2nd stamp. And there's a range. As long as it's still within this weight range, 2 stamps is enough. And if it gets above that, then you go up to 3 stamps or whatever. So postage is a great example of a greatest integer type function. You know, everything between these numbers is the same price, and then it'll go up after that. All right. So I just wanted to kind of look at an example of when that might be used and see if we can draw a graph to match it. We're not going to try to write the equation or anything. We're just drawing a graph to match this scenario. So an express mail company charges $20 for a package weighing up to 2 pounds and $2 for each additional pound or fraction of a pound. Let y equals c of x represent the cost to send a package weighing x pounds. Graph this on the interval 0 to 6. So we need a graph. All right, my x's are going to go up to 6. You notice on my interval, 0 starts with a parenthesis. What kind of circle are we going to start with on the graph? Open circle, good. All right, x here is pounds. Y is the cost in dollars. Okay. What's the lowest I would possibly pay to mail this package? $20. That's the cheapest package they have. Okay, so at 0, 20, I'm going to start with an open circle. And if your package weighs 1 pound, how much are you paying? $20. If it weighs 1.5 pounds, 20. If it weighs 2 pounds exactly, 20. But after it goes above 2 pounds, you pay extra. So we're going to stay here until we get to 2. For anything between 0 and 2 pounds, it's a flat $20. But after you hit that 2 pound mark, what happens to my price? It goes up $2 for each additional pound. So after 2, it'll go up to $22 until I get to where? 3. We have to keep it as a function, so it has to pass the vertical line test. So since this is a closed circle, I'll put an open circle here. And we're going to stay there until we get to the 3 pounds. So at 3 pounds, you're still just paying that $2 extra. But as soon as it weighs 3.1 pounds, they're going to tack on another $2. So it'll go up to 24. And then once you get to 4 pounds, after that it's going to go up to 26. And after you get to 5 pounds, then it goes up to 28 until you get to the 6 pounds. Okay. I want to look at the graph of x equals y squared. Can I graph that on my calculator? No, because it's x equals, not y equals. So if I wanted to make a t-chart, would it be easier to plug in values for x or for y? Probably the y, because then I can just square them and get x. So I want to put in a good amount, some negatives, some positives. So if I put in -2, -2 squared is 4. -1 squared, 0 squared, 1 squared, 2 squared. So what's the bottom? So we have 4, -2, 1, -1, 0, 0, 1, 1, 2, 4. What is this? You connect the dots, what does it look like? Sideways parabola. So is it a function? No, it fails the vertical line test. So remember, a parabola is x equals y squared. I flipped my x and y and then turned my graph on the side. Okay, there is something else I want to do, but I think I'm going to give you a few minutes to work on the